Hello everyone and welcome back. We finally reached the denial of service section of the course, and here I'll explain to you how our smart contracts can get exploited to cause denial of service. So, see you in a slide deck. Alright, so let's begin. Denial of service happens when the whole or parts of the protocol stop to function. It means that if we have a smart contract and because of certain bug, our whole smart contract stop functioning, or some crucial functionality stop to function, such as withdrawing funds, depositing funds, or something else, depending on the logic of our smart contracts. And there are some possible causes such as logical vulnerabilities, like in case of near storage bloating, prepaid gas exceeding, log event bombing. So I'll just go over each one of them and explain to you how everything works, and then we'll jump into the code and I'll show you those examples in action, and also show you how you could just write POCs in workspaces RS. All right, so usage of unverified accounts. Honestly, it's more applicable to older versions of Near SDK. At least that's what I saw so far. So as far as you know, accounts on Near follow certain rules described in this link, like length, like syntax, grammar, and so on and so forth. So if operations such as creation of account are performed on unverified account string, it will inevitably cause panic. So if we have something like, I don't know, let's say a dot 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 and something else after this, it's not correct account in here. So if we try to use some internal functions to register this account, like a create account function, this function will throw panic. So we won't be able to do this. It's advised to use account ID type when we accept accounts. And if we're using version 4.00, it will automatically enforce the validity. So we don't have to deal with this much. And depending on protocol's design, this error might lead to denial of service. So here's a case study. I did an audit on Octopus Network Appchain Registry a while ago, and I discovered couple of critical vulnerabilities there, and one of those was actually a logical denial of service due to how they handled accounts. So they weren't verifying accounts, caused denial of service. So just to give you a quick overview, what the hell is Appchain Registry? So you, as a project, want to register in their Appchain registry, in Octopus Network Appchain registry. You can think of it as App Store. So you give them all of your metadata, such as GitHub URL, project URL, website, account ID you want to use, and so on and so forth. Then Octopus Network manually verifies the correctness, and if all good, it'll just add you to a queue, and in that queue, you just stay and wait for other people to vote for you. So people want to see you in their Appchain registry, they'll begin voting for you, like giving their tokens to upvote or downvote, and depending on amount of votes, you'll move to deployment stage where your chain gets deployed in Octopus Network ecosystem. Octopus Network is literally just you have substrate chains, and instead of deploying to Polkadot, if they're super specific to one need, it might be cheaper for you and easier to you to go and deploy on Octopus Network. So that's the whole purpose of Octopus Network. So as I explained before, Appchain teams submit all those data, Appchain ID, website URL, GitHub address, and they vote for candidates. And during certain periods, votes are concluded using conclude vote function. At the top, Appchain with a majority of upvote gets registered as a sub-account. So we have Octopus Appchain registry.near, and our supplied Appchain ID gets registered like this. For instance, my Appchain.Octopus Appchain registry.near. So what's the issue? Unfortunately, Octopus Network team wasn't verifying the validity of Appchain ID, even though they technically were doing this manually. But we think about the smart contract, and from the perspective of smart contract, it's super critical, since if we have a human error, and we just didn't think that chain ID is invalid, it just gonna pass through and just cause denial of service of critical functionality. So it's not ideal. So basically we have a conclude voting score. And what happens here is owner calls it during like certain periods. And then we get top Appchain ID in queue, get current account ID, like Octopus Network Appchain Registry, and get top Appchain ID in queue. Let's say in our case, it's my Appchain dot Octopus Appchain Registry dot near. Then we just bring them together with a dot, and that's going to be our sub account ID. Then it goes here to this function, create a promise to create account and add access key. So that's pretty much it. That's what happens. And then afterwards, the top Appchain ID in queue gets removed. So that next voting can continue and next Appchain ID will be registered also. But imagine that Appchain ID is not correct. So when we do conclude voting score, we get this account. It's just a string in this example. It's just string. I mean, it doesn't have any validation whatsoever. So, and then we have like incorrect string in here. And then we move and try to create account with it. Obviously, near is smart and it will cause panic saying that it's incorrect account ID. So in this scenario, and you cannot remove the top chain ID in queue. So there is no way for you to conclude votes anymore because you cannot remove top Appchain ID in queue, and top Appchain ID in queue is always going to be incorrect account. So you won't be able to do anything with conclude voting score anymore. So that was pretty much the root cause of the whole issue. So if you add validation to Appchain ID, you won't accept it in the first place, and it won't ever become top chain ID, Appchain ID in queue, and then it's going to get solved. Because if you're going to be causing panic in here, top Appchain ID in queue won't get removed ever. So you basically have denial of service on conclude voting score. So yeah, that's pretty much it on the root cause. And again, if you want to read more, just go to public report in Octopus Network, public report in Halborn's repo. So let me move on to storage bloating. Storage is not free, so you have to pay for storage in near, and you pay roughly 1 near for 100 kilobytes of data. And if for some reason cost per storage write is more expensive than the smart contract gain per storage write, then it opens up a possibility for malicious actor to bloat the storage with dummy data and cause denial of service because you won't have enough free balance to cover storage anymore. And what I mean by smart contract gain per storage write, I mean that we get 30% gas fees back. And also if someone deposits any money, we also get this back. So that's what I count as a gain per storage write. That's why we should always measure this. We always have to keep track of our free balance, and we always have to charge users to deposit something to our storage, get like a basic amount of storage deposit to make sure that it's not financially viable and like literally impossible for them to cause denial of service in our smart contracts. And to understand whether a certain function is vulnerable to this attack, we have to do some calculations. So first, we calculate storage per write. Storage per write is amount of storage written every time user calls this function, like any function. Cost per storage write in near is storage per write divided by 100,000, since 100 kilobytes of storage is roughly 1 near. Then we are getting contract gain. It's contract balance after minus contract balance before, since contract earns roughly 30% of gas fees every time user calls the function, plus some deposit if user deposited something. And then we check if contract gain is smaller than cost per storage write in near. And if that's the case, function is vulnerable since contract earns less money than contract spends on keeping that storage every time user calls this function. So it's more expensive for smart contract to keep a new storage through this function compared to amount of money contract gains. And then afterwards, we can estimate the cost of an attack on a vulnerable function. In this sense, we get initial storage cost, just a starting point. We are trying to understand how much money does the contract need to maintain current storage? So we get current storage and we divide it by 100,000 since 100 kilobytes of storage is roughly 1 year. Then we get free balance. So we get contract balance before attack and divide it by 1 year to get the balance. And we just do minus initial storage cost. So we get amount of balance smart contract has now, and then we just subtract the storage cost to maintain. And then it's going to be our free balance that we can freely spend and transact with. And then we calculate the attacker spend per write. So amount of money attacker has to spend every time he or she calls this function. So just balance before minus balance after divided by 1 year. And then at the end, we have cost of an attack. So it's, in simple terms, number of writes multiplied by attacker spent per write. So it's free balance worth of data divided by storage per write. And how free balance worth of data is calculated? We get free balance in year and multiplied by 100,000 to get it in bytes. So now we have an idea about current storage amount of bytes that the smart contract has, and we try to divide it by storage written every time attacker calls this function to understand how many iterations we have to do to exhaust the free balance. And then at the end, we just multiply it by attacker spend per write to get an idea how much overall money attacker has to spend to cause denial of service on this contract. So here is just a simple example. When we call add new here, we just basically we are inserting user data to the storage, and eventually it's going to cause denial of service because we won't have enough storage to cover it. So that's pretty much it, super simple. And prepaid gas exceeding. Currently, the maximum prepaid gas that can be attached to a smart contract is 300 T gas, and exceeding this will cause the call to fail. And obviously, it's super common when public function performs some operations by iterating over storage. In that case, the smart contract might not have enough gas to complete this operation, and it will cause denial of service. Imagine we have a lot of accounts in the storage, and then we have a function called iterate all. And then someone calls iterate all. And it's because we have so many accounts, smart contract won't be able to go over every single one of them, and it will exceed the prepaid gas. So usually what you could do is just set limit how many iterations you want to get, or if you have a view function that lets users to get certain amount of accounts or data, you may decide to put some limits. So otherwise, in this scenario, eventually no one will be able to call this function. Log event bombing, max events that can be emitted in a single transaction is 100, and exceeding this limit will cause the call to fail. Again, it's super common when you are iterating over something, like in this example. Here it is. We just have a log, and when every iteration happens, we just log something on chain, and eventually, if we have more than 100 accounts, it will cause the call to fail. And in this scenario, since we don't have any limits, no one will be able to call this function and get the data, because eventually it will just panic and we won't have, because the maximum amount of logs you can have is 100, meaning that max accounts that you can have in storage in this scenario is also 100. So, all right, so that's pretty much it for the denial of service slide deck. And as you can see, the next one's a race condition, so it's interesting. And yeah, let me jump into a code so I can show you nice examples in action. Okay, welcome back to a code. So you have access to this inside of DOS folder. And the example is super similar to access control one. It's literally exactly the same, but we added users field to our contract struct. And here we also added register user and register batch functions. Register user function literally just adds users to user account to a storage and logs it. A register batch iterates over user's vector that we supply and registers user using this register user function. So first we're going to exploit the storage bloating issue that we have in register user function, and then we'll move to log bombing through register batch. So let's start with register user exploitation. So we have just prepared DOS, exactly the same as access control. We create some accounts, then deploy them, then initialize it and send contract and caller back. So let me just go to exploit those register user. We get our contracts and caller back, and then we first transfer some near from those contract to caller. The reason behind this, we don't want to wait 1 or 2 hours until exploit completes, because initially contract has plenty of money to cover for its storage, so it's going to take a while until it reaches the point when smart contract can no longer support its storage. So that's why we are transferring 18 year from the contract to caller, so that we can just wait roughly 5-10 minutes for exploit to complete. So then I'm asserting that transfer was success. Then I'm generating account with basically it's A repeated 60 times, since the max length of an account is 65. So I'm generating 60. And that's also the reason I'm starting with 1,000 till 10,000, since in the 10,000 case, it's going to be 61, 62, 63, 64, and 65. So it's still cool and it's still going to work. And then I'm just formatting everything so that it looks like an account, appending everything together. So we have generator, like gen, like 68, and just iteration number. The beginning is going to be 60A and 1,000. And then we just call the register user with account, and that's all pretty much it for the whole exploit. And the rest are calculations, as you can see from here. And at the end, I'm printing some important data so that we can see how everything works in real world. Like we have cost per storage rack, attacker cost per iteration, storage added, contract storage cost, contract gain per iteration, cost of attack, and free balance. So let me first actually run this so that you can see how everything changes in action, and then I'll go over the calculations so that we know how everything looks first. Let me run it. I just put it here, I move it here. Okay, we deployed denial of service contract. Now it should start. Right, as you can see, we started adding stuff. So we have cost per storage, right? I don't know why it's formatted like this. Maybe because I changed how it looks in here. Anyways, let me just reformat it so it looks better. Otherwise, it looks ugly. We just do them like this, this. Sorry. This, and like this. Oh, it should look good, I guess. Just restart it. Yeah, it always happens when you try to give demo. Like something just doesn't look good or work. Okay, just let's wait a bit. Oh, it should look good. Okay, now it looks a lot cleaner and better. So, okay, so we have cost per storage, right? And as you can see, that's amount of near smart contract spends every time we add something to a storage. And this attacker cost per iteration, And it changes depending on the gas, obviously, and some additional stuff. We literally just take balance before, balance after difference in here. Storage added, that's 260 bytes, 236 bytes of storage added every time we call this function. Contract storage, and that's contracts storage every time we call this function. So as you can see, it always increases. So you can just monitor this and you can see that contract storage increases every time we call this function. So add the contract storage cost, and you also should see that it also increases respective to this. We just make a little conversion of this to near in this scenario. So, and we can see contract gained per iteration, and that's amount of near contract gains every time we call this function, basically from gas fees. And here is the cost of an attack. And it also decreases. If you want to see cost of an attack before launching, you can just scroll up to the first one, and the overall cost of an attack is that amount of near. And every time we run the attack, cost of attack decreases. And free balance also, as you can see, it also decreases since we have more storage and more storage costs. So the free balance also decreases. And eventually, when cost per storage write becomes larger than free balance, we're going to see a denial of service, and smart contract won't be able to handle any storage writes anymore. So we have to wait until cost per storage write becomes larger than free balance. So I'll just pause the video and start again when it finishes. All right, so exploit has finished successfully. Been roughly 5 minutes, I guess. Anyways, so as you can see, we got an error back saying that lack of like balance for state. So if we then try to call something that adds data to a storage, we won't be able to do this until someone goes and increases the balance of contract. So it's technically denial of service. So if you explore the latest log here, latest data, we can see that free balance now smaller than the cost per storage write. So that's when we actually got the denial of service and got an error of like balance for state. And if we move just one step behind here, it's still larger. So everything works in here. So if we go through calculations, I already explained calculations in the slide deck. And here, like for instance, I'm asserting that contract per storage add in near is bigger than gained per iteration. If that's the case, contract is still vulnerable. So the cost of writing to a storage is bigger than contract's gain from gas fees. So here's the cost of an attack. Here is like description. So we have free balance in near in bytes divided by storage written times per iteration cost, attackers per iteration cost. So we get number of iterations needed times attacker spent per iteration. And I just did multiplication before division to avoid some rounding errors in here. And then we also get like a free balance. So it's the contract's balance per iteration in near minus storage cost per iteration. And then here is just the free balance in bytes. So multiply it by 100,000 to convert the amount of near to corresponding amount of bytes. And here are just some like balance before, balance after, like we're getting contracts balance per iteration, account balance per iteration, then we use them to calculate spend per iteration, like mainly just taking differences and converting to near. And here we just check balance of a contract after calling the register user. And here we are just also checking the balance of account after calling the register user. So we check before and after calling the function. And here we are also calculating spend, as I also explained before. We're calculating gain, just calculating contract's balance after minus balance or contract per per iteration that we do in the beginning before calling the register user. And then we just move to cost per storage add. So storage per call, amount of storage added every call. And we just divide it by 100,000 to convert it to near. So yeah, that's pretty much it in this scenario. So let me move to log bombing. Let me first clear this so it just looks better. Awesome. So yeah, let me go to exploit those log bombing. In this scenario, we just also generate some accounts. Just have A with 60, and I'm just using a map to just generate bunch of accounts in the vector. Just again, similar concept as in the previous one, I'll just append some generator. Just 60 A's with iteration number. So like in the first one, it's going to be 60 A's 1, 60 A's 2, etc. So then we calling register batch with vector of accounts, and also I'm adding max gas so that we attach maximum number of gas to our call so it won't fail. And then afterwards we just assert that everything is success. But obviously it won't be success since maximum number of logs we can have is 100 and we do 101 in here. And if we explode the register batch, we're iterating over users. Then we're calling register user function, and as you can see, it inserts data and then logs it. So max amount of accounts we can have in the register batch is 100. More than this, we'll get log error. So let me just run it. Okay, as expected, we got an error back. So yeah, some data like a register user, the latest user registered is 60A and 100, and the 101 one caused a function called error. The number of logs will exceed the limit 100. Let me just here. So let's see. Yeah, the number of logs will exceed the limit 100. So yeah, we caused log bombing, and obviously it makes sense for first of all, take some deposit to register users and maybe add some additional checks to batch accounts so that it won't cause any additional issues, like in case of like just a log bombing in here. So, all right, that's it for this video. And I see you in the next lecture where I'll explain to you race condition and reentrancy in near.